privacy invasion or something, I guess. But yeah, the recording's loading up. And we're recording. There's a notification. Okay, cool. So yeah, we're gonna start. Well, I guess we'll kind of be going back and forth between the simulation I sent you and the Jamboard that I also sent a link to. And so what I want you to start with, and I guess I know you've seen this simulation before. Amy showed it to you in class one time, but I want to give you a chance to explore it a bit on your own. So I'm going to give you, let's say, like 5 or 6 minutes to just kind of play around with it, see what you can do. There's some things I will point out that can be helpful, can be cool. Well, these green buttons will start the taps when you press play, and you can see the waves there. The amplitude will tell you like how bright the waves are. I'd suggest putting it up to max because that's easiest to see visually. The frequency button here, you can play around with the frequency to see the kind of the space separation between waves. Something to point out is that if you click this button at the bottom, it resets the whole thing, so you don't have to undo a lot of changes if you want to reset it. And I guess the last main thing to look at is that you can also, here you can select different types of waves. So here I have sound waves going. You can make particle waves to show like the actual particles in air or in water or whatever, and how they would move. And lastly, you can look at light, and so you end up with like lasers here, and you can change the frequency, which I like doing the light one because you have different colors to different frequencies, and you can have light waves going. So what I want you to do is take like 5 or 6 minutes. Maybe if anyone else joins us while we're working on here, I'll give you a bit more time, and just play around with it. Play around with the different settings, different mediums if you want to. And as you're going through it, if you can, on this first slide of the Jamboard, just click the sticky note button and add some observations, add some notes, just some things that you notice, and we can talk about them after. You can add questions if you like, but just as you're exploring, as you're playing, add some things here. Questions, observations, just kind of, I don't know, taking notes on a cool background. We'll give you a few minutes to play around with that. I'll give you another minute or two of exploring things, and then we can move on to some of the discussion questions that I've planned. All right, there's a couple of good points here. Let's talk through those quick, especially for the sake of someone who's watching this after. So if you're watching this recording, yeah, we'll just kind of talk about each of these points for a bit, and then we can go through some of the questions that I've come up with. So one observation that you made was with higher frequency, the wave fronts seem to be closer together. Absolutely, they do. So if we do, let's do sound waves, for example, and we let it play like this, and then we increase the frequency, these patterns of bright and dark, which correspond to like a positive and negative amplitude, or compressions and rarefactions in the case of sound waves, which this is, then yeah, these spots get closer together for high frequencies and further away for lower ones. Nice. All right. What else do we have here? So lowering the frequency made the waves act almost like a single point source. Similarly, if the separation of the sources is reduced, it acts like more of a point source. Okay. For this comment about lowering the frequency, was there a particular setting you had this on that you noticed that more than others?
Oh, let me see. Sorry, for the second one?
For yes, the second one.
Lowering the frequency. Yeah, I pretty much just had the frequency set on the lowest setting, and then
okay.
Yeah, I was playing around with the separation of the sources.
Nice, yeah. So if we make this separation really small, then there's not much of an interference pattern, and the wave fronts kind of look like they're coming from one source. Absolutely. If we make the frequency really high, then we have it's a bit more obvious. We have some definitive lines of interference. That's a really good observation. Nice. We've also got that as the frequency is increased, the lines of destructive interference appear. Yes, and that's kind of what we were just looking at. With the lower frequency, it's harder to see that interference lines under certain conditions, of course. Okay, and this last point, there is a point where the number of destructive lines doubles. That's a really interesting one. And actually, that's not something that I noticed when I was playing around with this. Can you talk me through how to find that?
Yeah, I was I was on the water example.
Okay.
And I think uh, let me see. Yeah, changing. So I have my separation maxed out, and then
Okay.
if I'm changing the frequency from, say, like the halfway point,
Okay, like where it's starting at?
um, yeah, or even I don't know, even like the I guess I had it more at the quarter point, so like a quarter of the way along for min.
Okay.
So starting from there, there's two visible lines of destruction, at least in the viewport that we're given.
Mm-hmm.
And then if we move it up to like the 3/4 mark, um, the frequency up to the 3/4 mark, then we're seeing at least four, possibly two more up right at the top and bottom.
Mm-hmm. Yeah, right here and here. It's hard to tell in the simulation.
Yeah.
But yeah, absolutely. We've got these 1, 2, 3, 4 lines now. Nice. That's a really good observation. I like that. Thank you for bringing that up. All right, cool. So back over to the Jamboard here. At the top, you can go through slides. Let's go to the second slide. So I just took a screenshot of, well, I guess it's something pretty close, pretty similar to what you were just looking at with the water waves interfering. And I just want to clear some things up. So on this diagram, what I want you to try to do is indicate where is there constructive interference. I don't know why that's capitalized. It's bugging me. Where is there deconstructive interference, and where would you say the nodes are? And so to show this, you can, I think you can, yes, you can add lines if you want to show like a line of one type of interference or something. So that's kind of if you click the circle and then, oh wait, yes, you know what you're doing. What you're doing is excellent. That's probably better than trying to make a shape. Yeah, you can just draw it with this drawing tool here. And you can do some in each color to show which is which. That would be fantastic. And just to make sure you have the time you need, I'm going to give you a ready to continue message in the chat so that you can let me know when you're done and you're ready for me to keep going and talking about this. Okay, so we're ready to talk about this. So I see a constructive interference line right down the middle. So your constructive interference line, I'll draw one as well, goes, oh, this is really hard to do on a trackpad, goes right through the parts where it's going bright to dark to bright to and dark and bright and dark. Absolutely, because these bright spots are where both water waves are up, or like they're splashing upwards rather than being down. And so these bright spots are where they're overlapping and they're constructively interfering. They're adding up and getting even higher to make like a crest of a wave. The dark spots are the opposite. Those are equivalent to like the troughs of a wave. And some of this terminology is coming more from one-dimensional waves, but it's a similar idea where these dark spots are where both sources of waves are down or like below where the water level would be if there were no waves. And so they are also constructively interfering, but they are both interfering, or they're interfering, but they're both down waves, or troughs, like in the one-dimensional case. Deconstructive interference is where you would have an up wave and a down wave, or even waves that are they don't necessarily have to be at the crest and at the trough. You can have a wave that is partially that, I don't know, maybe has a small displacement, something like around here, kind of around the edge of one of these bright spots. It's blue, it's not black, so it's still above the water level before we started splashing. So this would be a little bit above that normal water level. And this kind of edge of the black part here isn't quite as dark as the middle, but it is still black. It is still dark. So that would be slightly below the water level, or what the water level would be if there were no waves. And so anywhere that these types of these waves overlap would be deconstructive interference, where you have one that's kind of up and one that's kind of down. So I'm gonna erase these little lines, or try to anyway. Jamboard can be finicky. So you'll get deconstructive interference that will be between your constructive interference. And so those are these fuzzy lines, because these fuzzy lines show where the wave that's above the kind of like the flat water level, and the wave that's below that water level, where they overlap and they cancel each other out. And so these fuzzy lines, I'll highlight two of them. You got another one of them up there. These fuzzy lines are where there's total deconstructive interference, and there would be some partial deconstructive interference in there as well. Okay, so lastly are the nodes, and I see you've got a couple of nodal lines there. Those look good. The nodes are going to be where there is total or complete destructive interference. So I guess that's where I drew my yellow lines as well. So we can have destructive interference that's only partial, and so that would be kind of in the vicinity of the nodes. But the nodes themselves are the lines that never change color. And so when you run the animation, there's these lines that are always kind of fuzzy. And those would be the nodes, because they're always, I guess the waves are always canceling each other out completely, and so the water level doesn't change there. Nicely done. All right, let's move on to the next slide. So for this slide, I took screenshots of, this was the light interference, which you can treat similarly to the water and to the sound as far as the interference pattern goes. And so I have two pictures. They're both light interfering, but I made some changes. In the simulation, I went in and I took a screenshot with one set of settings, and then I changed the settings a little bit, and I took another picture. And there's some clear differences between the top and bottom image, but what I want you to try to figure out, or guess, whatever, is I want you to try to figure out what property did I change, and what change did that affect. So, okay, I have cause and effect here. And so what I want you to write, and you can just write it on a sticky note and put it under the corresponding word. What I want you to write is a change or a difference between the two pictures. Which which difference is something that I would have changed, that I would have like caused explicitly, and what was the effect of that? If you have questions about what I'm asking, let me know. And otherwise, give that a try. I'll give you another ready to continue message. All right, I see some good comments. Let's talk about them. So the first combination here, your purple has a higher frequency than yellow. Absolutely, that is something that I went and I changed. So in the thing here, I went. Let's see. If I start with a yellow frequency. Oops, I should probably turn my lasers on. Yeah, so start with a yellow frequency, which has, let's see how many nodal lines it has. It has about 1, 2, 3, 4, 5, 6 nodal lines that are visible. And then I change it to a purple laser, and there are a whole lot more nodal lines. We've got 1, 2, 3, 4, 5, 6, 7, 8 now. And so absolutely, as you said, changing the frequency and changing the color of the laser is the change that that I did to it, and the effect it had on the interference pattern was that it made the wavefronts tighter. And so by tighter wavefronts, I assume you mean the distance like between two bright spots or between two dark spots is smaller. Absolutely, because with a higher frequency wave, whether it's light or sound or anything, you have a shorter wavelength. So what you're seeing, those tighter wavelengths are tighter wavefronts are the shorter wavelengths. And the effect that this has is that it creates more lines of destructive interference, specifically more nodal lines. Because remember, you can have partial deconstructive interference between those nodal lines, places where the waves cancel out, but not completely, because maybe one wave is up and one wave is like down or below the, well, I guess it's not water now, but one wave is down, but the size of one of them is a bit bigger at a certain position, something like that. But there's absolutely more nodal lines where the waves completely destructively interfere in the purple compared to the yellow. And so that was the effect of changing the wavelength or the frequency. Absolutely. Next you have, okay, so you said yellow possibly has a larger amplitude than purple, which would cause the yellow to be a brighter wave and so have taller crests and deeper troughs. That's a really good point. So absolutely, if I have here, let's look at a different color. We'll do a nice blue. Right now I have the amplitude maxed out, and so the blue is fairly bright. And if I decrease the amplitude now, we'll do something drastic here. These newer waves, or the more recent waves that are coming now, are quite a bit more dim. So absolutely the brightness, or I guess me changing the amplitude will affect how high the crests are and how low the troughs are, or will change the intensity in the case of light, or sound actually. And so in the simulation, that makes the wave fronts appear less bright. In the case of the yellow and purple light, I actually didn't change the amplitude when I was preparing this question, but the yellow does look brighter. And part of the reason for that is that because yellow is more in the middle of the visible spectrum compared to the purple, which is right at the end, your eyes are more receptive to yellow light because they're right in the middle of the visible spectrum, whereas the purple light, depending on a lot of things, since the purple light is much closer to ultraviolet, it can be harder to see. And so for that reason, it can appear darker. More likely the case is just that this program made the purple not very bright. But that's a good point. It's something good to point out. Mind you, when you get into lower frequency red light, it is showing it darker because it's less visible. So maybe there's a bit of truth to that, to this simulation as well. Okay, nice. Let's go on to the next one, the next slide here. I guess this is something we touched on already, but just to make it a bit more explicit, what did I change and how did that affect the simulation and the pattern? Here's two more pictures. And I want you to do another cause and effect table. We did already discuss this a little bit, so you can just jot down a quick summary of the differences between these. Oh, and I'm giving you another ready to continue message. All right, let's see. We're ready to continue. Let's take a look. So absolutely, the separation of the lasers is what I changed. And so these are, but I didn't change the wavelength, or in this case, the color of the laser. So they are at the same frequency, absolutely. But having the two sources spread out, or more separated, is providing more lines of destructive interference. Absolutely. When they're further apart, the waves have more lines, more nodal lines than when they're close together, even though they're at the same frequency and everything like that. Nice, okay. Let's see, how are we doing for time? 15 minutes left. All right, let's go on to this last slide here. This is something a bit different, but I just wanted to go over this. This was something Amy suggested it might be helpful to just kind of review. So what I have here are some tubes, and what I want you to do is draw, and just, it's hard to draw on this, but just give it your best shot with your mouse or trackpad or whatever. What I want you to do is, starting with a black pen, can you draw a standing wave, or like the fundamental standing wave, or like the I'm losing my terminology. Do you remember what the name is for a standing wave that isn't like a higher harmonic? Remember what the terminology is for that?
Yeah, it would be the fundamental frequency.
That, yes.
Or mode one.
Mode one. There we go. That's the name I couldn't remember. Thank you. Yeah. So can you sketch out as best as you can? I know Jamboard can be annoying. What would the a standing wave look like at the fundamental frequency? For each of these cases, so we're starting with a tube that's closed at both ends, just because it has a dark line at both ends. Next, there's a tube that's open at both ends. And third is a tube that's just closed at one end. So take a minute and try to do a rough sketch of what each of these would look like.
Apologies for my atrocious artwork.
I was just gonna say how good it is considering you're using Jamboard. Do you have like a drawing tablet or something, or are you just freehanding it?
It's just with my trackpad.
That is not
if I had my drawing tablet, it might be a bit better, yes.
Oh no, that is not at all atrocious. I'm about to show you atrocious. Okay, so we've got some lines. Nice. The first one looks fantastic. The case of a tube that's closed at both ends is actually just like a string that's fixed at both ends. So you just have the fundamental frequency. For the fundamental frequency, the standing wave pattern, it has one antinode, so one kind of maximum spot that oscillates up and down, and it's fixed at both ends. Now, this second one that you've got here, that actually looks a lot, well, that looks a lot like the first one, and that's not quite right, because in the second case, there's no walls at either end, so there's nothing to keep the wave fixed in the middle here. So there shouldn't actually be any nodes or any fixed points on either side. So in this case, what the wave would look like more, and I'll do my drawing in white. We'll see if that shows up. If there's no, if it's not fixed, then the wave would line up, kind of line up at the side, just like you have in this third diagram, actually, where you have the end of the wave goes from top to bottom of the tube. That's exactly what it'll look like if it's fixed at no ends. Although it'll be either at the top or at the bottom of both ends of the tube. So it'll end up looking something like this. Oh, I got so close. Something like that is the white line there. So I guess that's kind of one way it can go, and then the standing wave pattern would have a reflection, something like that. So if there's an end that it's not fixed at, whether it's both ends or just one, the string, no, well, it's not a string, but what looks like a string will go from the top and bottom of the wave, or of the tube. And so for this middle one, since it's fixed at no ends, you'll have it at the top on one side and bottom on the other side, or vice versa, or flipped. And that's the fundamental frequency as like a standing wave for this tube. This last one looks great though. You have it fixed. You have a node in the middle at the closed end, and your open end is oscillating top to bottom. Fantastic. Something I want to point out, just as a bit of a memory tool, I guess, for this middle case is that you imagine taking the standing wave pattern for a tube fixed at both ends and look at just half of this. So what I've traced over in white is actually the same pattern, kind of. It looks the same. It's the same type of pattern as this half of the right half, I guess, of the standing wave pattern in the tube with both open ends. And same thing, I won't sketch it out, but the right side, how it's, I don't know, it's almost like a greater than symbol. It is almost what it looks like. On this right side of the tube fixed at both ends, it's the same type of shape as this left side of the tube and its reflection for a tube with both ends open. It's a memory tool. If it helps you to think about it that way, go for it. Just thought I'd throw that out there. Let's draw the next harmonic. And I'm saying the next harmonic because it doesn't necessarily have the same number for all three cases. But if you were to up the frequency until you get the next standing wave, what would that look like? And can you please draw it in blue? I can distinguish it from the black. All right, nice. So in this this top, like the top tube that's fixed at both ends, we've added a node right in the middle here, absolutely. And now we have two antinodes, top and bottom. Looks good. And also just to point out, this is one whole wavelength here. This this second harmonic. Nice. Okay. Next we have, for this tube that is open at both ends. We have that the wave is always, like at the end, is always either at the top or the bottom of the tube. Nice. And so instead of having just the first node, like we had in at the fundamental frequency, we have 2 more nodes. Absolutely. And since we're increasing by 2 nodes, I think it's an M value that they call it in your textbook, increases by 2 each time. So you go from M equals 1, just with 1 node, and the next harmonic up, you have M equals 3, because you have to add 2 nodes at a time so that your wave, the standing wave pattern, can always be against the edges of the tube at the ends. Very nice. And lastly, we have here, oh, and one more thing to point out is that for the second tube, there is 1.5 wavelengths that fills it at this harmonic. And for the third tube that is fixed at one end, we still have our original node here where it's fixed. Fantastic. But we've introduced a node partway along the tube because for this second harmonic, we have one antinode now, and then a node, and then it sits along the top or bottom of the tube. Very nice. So it's almost 7 o'clock, so I think we'll end it there, just with a bit of a review about some open and closed tubes. And yeah, I guess that's it for today. So I'll stop the recording. We'll end that there.